Hello and welcome to this EPI-STEM instructional video on the use of the Polymers Active Learning resource. EPI-STEM is the National Centre for STEM Education in Ireland. It is committed to supporting STEM teacher learning through strong subject matter knowledge, research-informed practice and collaboration across professional networks. This Polymers Active Learning resource is underpinned by Kolb's cycle of experiential learning, also known as Kolb's learning cycle. Using Kolb's cycle in your classroom can support deep engagement with theoretical knowledge, provide a hands-on understanding of abstract ideas, and create a fun and engaging learning experience. As part of this experience, you're provided with the following 3D printable files: an atom and bonds. These simply slot together for use within the classroom in creating monomers. If you do not have access to a 3D printer, these models can be created using materials such as styrofoam spheres, wooden skewers and pipe cleaners, although these alternatives may be less durable with frequent use. This is a quick overview of the 3D printed files and materials provided. First, we can see the 3D printed hemispheres. They're created as hemispheres to make the printing process a bit easier. And to assemble these into entire spheres, we also provide small 3D printed cubes which act as a joiner in between. We can use needle nose pliers or simple tools like that to remove the support material after printing. We can also see here rigid bonds which are 3D printed. These would represent our primary bonds as they're rigid and non-flexible. If we were to use some flexible filaments such as TPU, we could also 3D print the secondary bonds which are less rigid. Here we have an example of the model put together. This of course only shows two spheres or two atoms and one bond, but this can be built upon into any number of combinations. We will now look at how the 3D printed parts can be assembled and used. When removed from the printer, the first step is to carefully remove the support material. This can be done using a pair of pliers. So once this is complete, the parts are ready to assemble. I have an example of two here. To assemble the model, simply place the cube that is given between the two hemispheres and push them together. Once assembled, students can then push bonds into these atoms to create monomers. Joining multiple atoms with multiple bonds can create a variety of different monomers. Students can then build on this further and turn their monomers into polymers by adding them together. Further to this again, they can also change from monomers to copolymers by combining various types of monomers. This example shows a simple structure consisting of two atoms connected by a primary bond. We can identify this as a primary bond because it's strong and rigid. To further develop students' understanding of polymers, we can introduce the concept of secondary bonds. For example, we could replace this bond or add an additional bond using a flexible material such as wire or pipe cleaners. This helps to represent weaker secondary bonds. An example of this type of interaction is van der Waals forces, which are weaker and can be disrupted by heat, causing the material to bend or change shape. This is similar to what happens when we heat acrylic on a strip heater. The secondary bonds weaken, allowing the material to bend without breaking. When we cool down the material, those secondary bonds rebuild and strengthen the material once more. Following the structure of Kolb's cycle of experiential learning, the accompanying slides guide students through four key stages: concrete experience, reflective observation, abstract conceptualization, and active experimentation. In the concrete experience stage, students engage in a hands-on activity, for example, building and manipulating the polymer models or creating slime. In the reflective observation stage, students are encouraged to think about what they observed what worked well, and what patterns they noticed. In the abstract conceptualization stage, students begin to connect their experience to scientific concepts and terminology, such as bonding types and material properties. Finally, in the active experimentation stage, students apply their new understanding, for example by modifying their models, testing ideas, or predicting how materials will behave in different situations.